Greetings everyone, my name is Asia Parker. I am from Duquesne University. This summer, I was in the SILI program and my mentor was Dr. Douglas Higginbottom. My project this summer was Modern Deuteron Form Factor Parameterization. In 2020, Brookhaven National Lab, partnering with Jefferson National Lab, will be adding components to convert the relativistic heavy ion collider, RHIC, to an electron ion collider, EIC. The first GIF is of the RHIC and the second GIF is of the RHIC converted into the EIC. The additional components will be the electron injector, injector lanic, electron cooler, and polarized electron source. The EIC applies polarized electron beams and polarized proton beams in order to probe the interactions between the valence quarks and gluons. The information obtained from these experiments will be employed to study the contribution of the hadron's constituents to the overall spin of the hadron. In the interior of the interaction regions of the EIC, there are crab cavities. The crab cavities are designed to apply a time-varying magnetic field which causes the charged particle beams to oscillate. This is known as crabbing. Here are the interaction regions that contain the crab cavities in the EIC. The following crab crossing animations were generated through Python using Jupyter Notebook. Then the frames were stitched together using FFmpeg into GIFs. The first animation is of the beams without crab crossing. As you can see, the percent overlap only reaches about 50%. The second animation is of the beams with crab crossing. The percent overlap reaches 100% because the beams oscillate perfectly so that they line up. Through crabbing of the beams, the luminosity of the collision experiment can be increased. The luminosity of the data is proportional to the number of collisions in an amount of time. Increasing the luminosity is high priority because it gives more opportunities to collect data on more processes during the interactions of the polarized beams within the collider. When using the EIC, deuterons will be preferred because they have a weakly bounded property that will aid in the study of free neutrons. The interactions within the deuteron are complicated and very long. Some form factors were introduced to make the calculations easy to comprehend. Essentially, form factors are viewed as the Fourier transform with respect to the scattering angle, or the most fundamental observables from a system. In previous deuteron-electron scattering experiments, data was collected and used to calculate the form factors. The data was later fitted using the Abbott parameterization. This parameterization worked for values within the experimental range, but when the range was extended, it had singularities. The Kiwi parameterization, designed by Dr. Douglas Higginbottom, when implemented, rids the data of the singularities. As you can see here, the Abbott fit 1 when approaching the values between 4 and 5 GeV squared for the magnetic form factor Gm has a singularity, but the Kiwi fit does not contain the singularity for extended ranges. The data fitting was done in Python using SciPy module optimized specifically the function curveFit. This curve fitting algorithm is done through the method of least squares and gives valuable quantitative feedback on the accuracy of the fit even when using an arbitrary amount of parameters in any possible fitting function form. The least square algorithm used by SciPy also contains an optional parameter for the error values of the data set in order to weigh the fitting function properly for both high and low values. The parameterization being done for this project will only contain the first 5 terms of the sequence, but because the code allows an arbitrary amount of parameters to be fit, this parameterization can be made more accurate in the future if needed. The data which was previously mentioned was loaded in from a simple text file using the NumPy Python library. The Kiwi fit, when compared to the Abbott fit 1 and 2, fits the data more smoothly. You can see this especially in graph 2 and with Abbott fit 1 at the start and Abbott fit 2 at the end. The data was also plotted on a log scale, which included taking the absolute value of the data. As seen in graph 3, the charge form factor GC crosses the axis, which is the dip. In conclusion, the Kiwi parameterization more accurately describes the extended data without singularities. Hopefully, the Kiwi parameterization will be used to make further predictions about the interactions of the Deuteron. Here are my references. Thank you so much for watching.